Good morning or good afternoon. My name is Atarut Azizin Amini. I'm the director of the ABC UTC at Florida International University. Before we get on the webinar, there are some important information and updates with respect to an exciting bridge conference that's coming up. We wanted to share with you. As everyone knows, 2022 International Accelerated Bridge Construction Conference, which is going to be fully in person, will take place in Miami, Florida at Hyatt Regency Hotel in downtown Miami, December 7 to 9. And please note that the early bird registration deadline now is September 2nd. So please take advantage of that a reduced rate for the registration. Also, on most of these slides, you will see a barcode. If you just take a picture of it, you can see the entire program, conference program. Also, we do have a travel scholarship program. These are only for the bridge professionals that are employed by the state or the local agencies in the US. It is not, this travel scholarship is only for the bridge professionals that are employed by the government agencies in the US. So please go to our website. It will give you all the details that you need. And it's a very simple application online that you can apply. So we hope that you take advantage of the travel scholarship to assist you to come and be with us during the December conference. Continuing education, the conference will give you a certificate that you can use toward the continuing education requirements in your states that you will have. Also, it is important to note that FIU is an official sponsor of the continuing education in Florida and New York. So we are approved providers. There is an award program. Again, if you go to our website, you will see the details of the different categories of the awards and the deadlines and everything else that you need and all the application that you need to fill out in order to apply your project to one of the awards. Just a note that this year we have a new categories. That's an international and also international case study, project. And also we have most impactful bridge engineering technology that have affected basically the bridge engineering. So 2 new categories for the awards. Day before the conference starts on Wednesday, December 7, we are going to have 4 workshops. These workshops are not just about the ABC. These workshops are for design of the bridges, steel bridge, design of the pre-stressed concrete bridge, design of the FRP bridge, and also a workshop on the Uhpc. So please take advantage of that. If you go to our website, you will see all the syllabus and what will be covered in each of the workshops. So for example, the workshop on the non-proprietary Uhpc is which Dr. Royce Floyd from the University of Oklahoma and Dr. David Garber from the Florida International University will be conducting, as well as the Dr. Mustafa from the University of Nevada, Reno will be covering. You can see that it includes many topics related to the Uhpc. There is an opportunity to exhibit at the conference. So there are we have had very several companies that are exhibiting, and I believe so far we are close to probably 30 exhibitors, but still there are booths available. If you like to showcase your products, services, please take advantage of this. And also, again, hope to see all of you. If you have enjoyed our webinars and all the other programs that we've had, we hope to see you in December in person. After a couple of years of pandemic, this is probably a time.
Our presentation today features the District of Columbia Department of Transportation's I-295 over South Capitol Street Bridge Rehabilitation Project. We're pleased to welcome our presenters, Connie Eskender, the DDOT Bridge Engineer, John Seifert, Associate Vice President with JMT, and Ben Cartwright, Senior Associate and Project Engineer with JMT. We'd like to also introduce our Q&A session moderators, Paul Lyles, former Georgia State Bridge Engineer, and Jugesh Kapoor with WSP USA and formerly State Bridge Engineer at WashDOT. We'll now begin our featured presentation. Connie?
Thank you, Marilu. This is Konnie Eskender, DC Department of Transportation Bridge Engineer. As shown here, today we will be discussing about the I-295 over South Capitol Street Bridge Rehab project. On the agenda, we'll have introduction, introducing the teams, DDOT's experience, and the I-295 over South Cap Bridge project, and Q&A session. So for the DDOT project, we retained JMT as the engineer of record and the designer. Corman was the contractor. Penn Stress was the fabricator. From DDOT side, Mnet was the project manager, and myself, bridge engineer. So as mentioned on the Federal Highway website, ABC improves site constructability, total project delivery time, material quality and product durability, work zone safety for the traveling public and contractors personnel. With that in mind, next slide. DDOT started using some of the techniques early in 2010, I'm sorry. And our first project was the Eastern Avenue over Kenworth Avenue. We used prefabricated columns for the substructure and prefabricated deck beam elements for the superstructure. In addition, DDOT used prefabricated deck beam elements for 3 other vehicular bridge projects, and one of them that will be discussed here today. In addition, FRP deck panels were used for 3 pedestrian bridges and 1 vehicular bridge. The first FRP deck panel was constructed in 2012. DDOT has used precast deck panels on other projects like the New York Avenue over the railroad and the Frederick Douglass Bridge over Anacostia River. This picture shows some of the projects. The left one is for Eastern Avenue over Anacostia Freeway or Kenworth Avenue. The top on the right side is for the Anacostia Riverwalk Trail FRP deck, and the lower right corner is where we used prefabricated deck beam element for the 16th Street Bridge over Military Road. Thank you. With that, now I'll give it to John. Thank you.
Thank you, Connie. I want to talk a little bit about the project location. Some of you may not be familiar. This is international, where Washington, D.C. is. So the project is located on the eastern seaboard of the United States in the capital of Washington, D.C. Within Washington, D.C., it is within the 8th ward, south of the National Mall, but yet near the Potomac and Anacostia rivers. As you can see in this satellite image of the project location, from the right, I-295 carries traffic from Maryland Route 295 from the right, and then on the left, I-295 flows into the interchange of I-495 right near the Woodrow Wilson Bridge, which will lead into Virginia. South of the bridge is you could see right around Martin Luther King Jr. Avenue. It's very densely populated. And to the north of the bridge is Joint Base Anacostia. So the original construction consisted of a 2-span, simply supported steel girder structure, very conventional type of construction for the era. This was an era during a lot of expansion of the highway system in the United States, post-World War II. As you can see, the bridge, the photo in the upper left, the 2-span structure. The bridge ratings were in accordance with the MBI, or National Bridge Inventory, a 5 rating of the deck and superstructure is considered fair, and the 6 rating for the substructure is considered satisfactory. However, the deck did have a lot of repairs done to it, and it looked like a quilt, some patchwork. The typical section below, you can see some of the conventional construction. The beams were rolled beams; they weren't girders, and they did consist of cover plates, which are really no longer used due to fatigue issues. In fact, I believe it was the Southbound bridge was estimated to have approximately 6 years left based on the fatigue criteria and rating. The concrete abutments and piers were of the conventional type of construction for the day, consisting of joints over top of them. And being in Washington, D.C., the area is prone to snow, and so de-icing salts get in there, and when the joints wear out, the de-icing salts get down in and they start to corrode, lock up the bearings, and begin to destroy the end of the girders. You could see the photo on the left of the screen. That's one of the girders, not near one of the bearings, but you could see the deterioration of the girder flaking off of rust. So we went out and did a hands-on inspection in 2015 to corroborate the biennial inspection findings. And during the inspection, part of it was we took cores of the existing deck and substructure, and we tested those for chlorides. And the samples did come back with deeper chloride penetration than what is recommended. We also did a petrographic analysis, or a test, and the bond of the cement paste was compromised, and the depth of the carbonation was excessive. So all this leads to the Lfd rating. During the rating, the existing structure was rating below a 1 for Lfd, which certainly wouldn't do if the structure were to be brought up to LRFD standards, which was one of the goals. The substructure strength, we thought about several techniques on how to increase the existing condition, and we were thinking of techniques like carbon fiber wrapping, so your conventional concrete repair and some crack injection type work. So our recommendations were to replace, obviously, the existing superstructure and rehabilitate the substructure. The cost to do the ABC was approximately 20% more, and I think the total contract price of the project was $6 million. So it's about $1.2 million additional cost to do the ABC method over conventional construction. However, J&T did do a loss of public benefit, or a user cost study, and it determined that the cost incurred by the general public, such as a long project duration with longer commute times, increased fuel consumption, more wear and tear on vehicles, and so on, show that the user costs were exceeding the ABC cost. They were approximately about 1.5 to 1.6 million over the conventional construction, making ABC really the clear choice for this project. So strengthening and repair of the existing substructure, again, I had mentioned FRP was the way that we were going to fiber reinforced polymer, and conventional concrete repairs along with crack injection. There was some new roadway signage, which made things a little bit more clear for motorists. And some of the drainage improvements that were provided for the project were really channeling water at the pier because we really couldn't change the configuration, the framing of the where the substructure units were. So we had to deal with a joint at the pier. We did a partial demo of the back wall to allow for a deck over, and the deck over allows for water, the joint to be behind the back wall, and therefore water can't get down into the bearings. In addition, between the two bridges at the approaches, a stormwater pond was put in place. The existing bridge width was really no good for two-stage construction and to maintain 11-foot lanes. So the construction was done in 3 stages. DDOT wanted the existing stone veneer to remain for this structure, so we kept that in place. As you can see there, the ADT for this structure was over 40,000 in each direction per day, and the average daily truck traffic was 5% of that. The other projects in the area, this became a little complicated. The Malcolm X interchange was being constructed concurrently and provided many challenges. The coordination of construction activities was a must for the ABC project to work out. So both projects, more so on the contractor on our project, had a very conscious effort to coordinate their construction activities. And often they had to share lane closures in order to make that work. So we had good cooperation out in the field between different construction projects. The other constraint with the project was that the skews are so substantial on this project. The bridge is on the baseline of the bridge is on a radius and the roadway is on a radius, but the girders are straight. So with simple spans, we have different skew angles at the end of each girder as we go along the bridge. And the girder lengths are between 50 and 78 feet. And the skew angles, which were, again, all different, varied from about 32 degrees to 46 degrees. Again, the goal of the project really was to eliminate the structural deficiencies, increase the durability by conventional repairs, crack repairs, and carbon fiber wrapping. And maintaining traffic without major delays and impacts was a huge issue within the for DDOT, because they wanted to impact their community as least as possible, but yet get the bridge done. Here are the typical sections of the weekend and weekday traffic. You can see during the weekend traffic pattern, all traffic was shifted to one construction zone, and 2 lanes of traffic were under, I'm sorry, I said that wrong. 1 lane of traffic, and the rest of the bridge, which would consist of the other 2 lanes, was under weekend construction. During weekday, there were always 2 lanes of traffic open and 1 under construction. So the I-295, the reductions to the 1 lane over the weekend closures was limited to 4 weekends. So a really tight window to try and get all of these sections in. But the impacts to South Capitol Street were also evident. So we had to close South Capitol for 2 weekends, really to get a lot of the FRP work done and some of the structural work to the abutments. And then we tried to do some off-peak work for South Capitol, closing 1 lane and restricting it to nighttime work. So here are some of the detours that we had, and I'll quickly go through these. The first detour, the I-295 northbound detour, had an issue because we had no other choice, but we had to go through the neighborhood in order to detour around the area. And so this took I-295 northbound over Overlook Avenue, and then a right on Chesapeake Street, and then another right onto South Capitol, and then back onto I-295. The I-295 southbound detour was pretty straightforward. We were lucky to have a virtually no turn option to get off and back on. So you would get off on South Capitol Street, straight on Overlook Avenue, and then back onto I-295. So the detours on South Capitol Street were fairly similar. The South Capitol Street northbound detour was allowed you to get around the project in a fairly quick fashion. You would get off onto South Capitol to I-295, exit onto Malcolm X Avenue, which was the part of the other project under construction, and then a right onto South Capitol. When South Capitol was closed, the detour, the southbound South Capitol detour was the longest, coming off of I-295 along Overlook Avenue and left onto Chesapeake Avenue back down into the neighborhood. So as you can see here, the times for the detours, the I-295 detours varied quite substantially from southbound to northbound. And likewise on the South Capitol Street detour, varying anywhere from 1 to 4 minutes to 7 to 12, depending on which direction. So at this point, I'd like to turn the presentation over to Mr. Ben Cartwright to discuss the ABC techniques.
Thanks, John. I will be talking a little bit more about the technical details of the accelerated bridge construction that we did on this project. Our ABC construction utilized what we called precast modular units, and these units consisted of 2 girders per unit with a cast-in-place deck. We used 5 units per span, so between both bridges, this totaled 20 individual precast units. As John mentioned, there were skews, heavy skews at each abutment and each pier, and they all varied. As a result of these skews on each unit, we had to show individual units, individual skews at each corner of the precast units. The contractor had the option of precasting the exterior barrier or casting it in the fabrication plant. He ultimately elected to have it fabricated at the plant. This presented some additional design checks for us. As the engineer of record, we had to check for overturning of the exterior unit due to the heavier barrier weight, as well as cracking due to the overturning moment. Luckily, there were no issues with this option. The image here shows the detailed units that we provided to the fabricator on our design drawings. As I mentioned, we had to show 4 individual angles at each corner. We showed elevations at each corner. We provided the dimensions along the skew, as well as the individual girder lengths. Each girder on our project was a unique length, so there were no cookie cutter shapes that we could use. JMT Survey Group completed an as-built survey prior to our design, which we used to obtain those beam lengths and get the skew measurements. This information was paired with a detailed set of deflections and cambers for each individual modular unit, which we provided to the fabricator. The fabricator was ultimately responsible for the overall fit of these modular units. The contract specifications required a mock layout to be performed at the fabrication site to ensure that these units would be fit correctly within our geometric footprint. JMT provided 10th interval points for the cambers and deflections. The image that you see on this slide shows a sample from one of the shop drawings. The fabricator ultimately relayed the cambers that he obtained at the plant back to us to compare with the cambers that we showed on the plans. We had to ultimately check that these camber differences were all within a reasonable tolerance. In addition, we had to check the adjacent units, particularly the exterior versus the first interior, to make sure that the vertical alignment between the two wasn't too drastic so that a closure pour would be uniformly installed. The abutment fixity condition was altered from the as-built construction. Originally, the abutment consisted of a fixed abutment at abutment A and an expansion abutment at abutment B. JMT ended up proposing to use fixed bearings at each abutment, and there were several reasons that we did this. As John had mentioned, we could incorporate a cast-in-place deck over that could be utilized to transfer drainage behind the abutment. I'll touch a bit more on that in a future slide. Secondly, any discrepancies could be taken up at the abutment. The deck over allowed any lateral misalignment at the unit ends to be basically covered up. All the joint rails at the pier could be aligned more perfectly because it was set at the pier first, and then discrepancies could be made up at the abutment. Lastly, any misalignment of the anchor bolts could be re-drilled and grouted as necessary at the fixed abutment. We did have a few isolated locations where the pre-drilled anchor bolt holes were not aligning, and we did have to re-drill and grout, but it wasn't an issue because the abutment was fixed. The pier fixity condition was also changed from the as-built construction. Originally, piers had one line of fixed bearings and one line of expansion bearings. JMT ultimately proposed to use two lines of expansion bearings at the pier. And there were several reasons that we did this. First and foremost, we wanted to relieve some of the thermal and longitudinal loading on the pier. As John had mentioned, the substructure rating was less than 1, so we really wanted to get the loads down. The expansion bearings at the pier allowed us to do this. Secondly, a strip steel joint could be used for the drainage, similar to the as-built condition. We did have some flexibility in installation due to the strip seal and trough material, which was a little bit more lenient, so it helped with the overall fit and alignment of the units across the pier. As I mentioned, the units were first set at the pier, which allowed the joint rails to more accurately line up. And as I said, all discrepancies would be taken up at the fixed abutment. The image on the lower left is a clip from our design plans showing our typical joint detail, the steel extrusion or rail. And the image on the right shows how we created a uniform rail through the closure port area. We detailed the rails to be extended beyond each individual unit. Then we allowed the contractor to field cut these rails, install a new piece of rail, and then bevel groove weld everything all together. We proposed a ultra high performance concrete pour to tie all the units together. This is also known as Uhpc. This type of construction is very common when using accelerated bridge construction. In our design, we specified a design strength of 14,000 PSI at 24 hours and a 28-day compressive strength of 21,700 PSI. Originally, we had proposed a 3/4 inch PPC or polyester polymer concrete overlay to create a uniform riding surface. The contractor ultimately proposed a 1 1/4 inch latex modified concrete overlay. LMC is about half of the cost of PPC, and the contractor was a bit more familiar with this type of installation, so this was ultimately approved by DDOT. But as a result, JMT as the designer had to adjust our bearing seat elevations. We also had to recheck our design and ratings, and we had to double check our deflections and cambers for the extra overlay thickness. All these changes were satisfactory, and the changes were ultimately very minimal. So this all worked out in the end. The lower left detail is a formwork detail for the closure pour. This consisted of a coil rod assembly on the top and bottom with timber formwork. The coil rods were ultimately removed, and we had the contractor fill the coil rod voids with epoxy grout. Now I'll talk about some of the diaphragms and connection plates we used on this project. We ended up proposing channel diaphragms throughout. The diaphragms between adjacent modular units were field installed after the closure pour had been made. All holes in the diaphragms were shop drilled. All holes in the connection plates were field drilled. And the field drilled holes allowed the contractor some greater flexibility when installing. The image on the bottom is a completed installation picture that shows the intermediate diaphragms, which were installed normal to the girders, and the end diaphragms were installed along the skew. The skew diaphragms were installed using a bent connection plate, as you can see on the detail on the right. The bent connection plate had to be fabricated to the skew of the bearing lines. So the as-built survey and comparing with the as-built skews were very important to make sure that the connection plate was installed correctly and that the channel diaphragms were going to fit up correctly. Now I'll discuss some of the drainage considerations that we encountered on this project. The existing bridge had scuppers near the abutments, and the downspouts were actually cast through the abutment concrete and drained near the top of the footing. We ended up eliminating the scuppers on this bridge. Due to the inability to use a continuous beam due to the loading on the substructure, we ended up using, as John mentioned, another open joint at the pier, similar to the as-built condition. We proposed the strip seal and trough as shown, with the downspout that emptied the water beneath the bridge structure. Again, the abutment joints were relocated behind the abutment back wall, and this prevented water from seeping onto the abutment bearings and prolonging the life of the abutment structure. We used a 3-inch diameter perforated pipe which ran parallel with the back wall, and outfall pipes were spaced at approximately 10 feet, which carried the water to a porous backfill behind the abutment, which you can see in the yellow shade on the image to the right. There were also some electrical considerations on this project that we had to incorporate into our design as well. The exterior bridge parapets included both a 4-inch diameter conduit and a 2-inch diameter conduit for electrical and utility needs. Our underbridge lighting was replaced with new LED lighting. JMT's engineers determined that a 2-inch diameter steel pipe duct would need to run parallel with our back wall and ultimately turn up through the deck and into the proposed junction box in the cast-in-place portion of our deck over. So this location of the steel pipe duct had to be carried through 3 separate concrete pours as shown in the picture, through the cheek wall, through the deck, and then through the parapet. And this duct had to pass through a lot of congested rebar and ultimately into the exact desired location of that junction box. The image on the right shows the as constructed image of that junction box. In order to complete this project, the contractor would ultimately need to complete a lot of work within a short weekend period. These weekend periods were what we ultimately called the critical weekends. At 9 p.m. on Friday night, the contractor would have to shift all traffic to a single lane and begin demolition and installation of 3 units per span, which would accommodate 2 lanes of traffic. By 4:30 Monday morning, the newly constructed bridge, closure pour and all, would have to be reopened. So JMT provided a list of construction activities that would need to be completed in this time frame in our contract plan so that the contractor was fully aware of what work needed to be done within that time frame. JMT's construction management team thoroughly reviewed each work item and ensured that we were allowing enough time to complete all of the work required. And in addition, there were steep penalties for the contractor not reopening the bridge by Monday morning at 4:30. And these penalties amounted to $1,500 per hour on the southbound bridge and $10,000 per hour on the northbound bridge with no upside limit. Luckily, this disincentive was not used. The contractor ultimately completed all work on time. The abutment and pier cap rebuilds were necessary on this project to accommodate the new girder layout. The image on the left shows a hatched area that represents the removed portion of the existing pier cap. The shaded area on the right shows the rebuilt portion. The cap rebuilds also required new reinforcing steel. At the top of the cap, we added a new layer of reinforcing bars, and we also drilled and grouted new U-shaped bars into the existing caps to enclose those new transverse bars. The existing superstructure used 8 W beams. JMT ultimately proposed 10 plate girders. This increase in beams allowed us to reduce the overall superstructure depth, thereby increasing the vertical underclearance on South Capitol Street. Similarly, the existing bearings used steel shoes, which were over 9 inches tall. JMT proposed elastomeric bearings that were only 3.5 inches thick. These two design elements ultimately allowed us to increase the vertical clearance from 14 feet 11.5 inches to 15 foot 4 inches on the northbound bridge, and from 16 foot 1 to 16 foot 5 on the southbound bridge. So we were overall able to add about 4 inches of under clearance on South Capitol Street. Once the piers were changed to 2 lines of expansion bearings to relieve the thermal and other longitudinal loads, we still needed some extra shear and moment capacity in the cap to bring the entire substructure up to current LRFD code. This was also due to the new bearing alignment once we changed from 8 as-built girders to 10 proposed girders. So the reactions were now located at different points along the cap. As John had mentioned, we propose using carbon fiber wrap reinforcing on the pier caps. The shear deficit was about 22.5 kips, and the positive moment deficit in the cap was about 24 kip feet. JMT ended up running some initial calculations for the carbon fiber wrap, and we determined that a 3-foot wide band on the cap outside the columns would be required for shear, and then another single layer of carbon fiber wrap on the underside of the cap would be enough to satisfy the positive moment. And this image here shows the contractor applying the stain to the substructure, but you can also see the carbon fiber wrap installed already adjacent to the column. We had a lot of lessons learned on this project, and I'll discuss a few of them now. First, it's extremely important to check, as I mentioned, the accuracy of the field survey against the as-built plans. It's important to check all dimensions, angles, beam lengths, bearing elevations. You want to make sure that everything is within a reasonable tolerance. And if a dimension is out of place, it's best to check with the survey group or even request additional measurements. You don't want to find out that you have a bad dimension once the units are in the air and ready to be installed. Next, consider what an alternate wearing surface or barrier type might do to your cambers. As I mentioned, we had to recheck our cambers when changing from a PPC to an LMC overlay. And luckily, the changes were insignificant, but it's always something good to think about during design. What could possibly change in the field, or maybe you should add some extra haunch to your beams just in case there are deflection issues in the future. Next, we'd recommend to use an experienced engineer to check the shop drawings. Our shop drawing review went through 3 to 4 rounds of rigorous review and constant communication with the fabricator, which ultimately allowed us to be completely comfortable that the fabricated units were going to fit within our complex geometry. Next, during design, we would suggest to try and anticipate how your discrepancies or misalignments will be handled in the field. The units, even after fabricated, are going to twist and warp through shipping and storage, and what is installed is never as anticipated. In our case, our deck over detail at the fixed abutment allowed us some greater flexibility in taking up these misalignments. As I mentioned, we also had to pre-drill the anchor bolt holes in the fixed abutment However, in hindsight, we maybe could have used cans to reduce the need to re-drill and grout and even avoid the rebar in the tops of the caps. Lastly, we would suggest to prepare for construction issues ahead of time. It's really important to think about things like how the units will be lifted. For instance, we found that the lifting devices were overstressing our flanges, and the contractor had to prepare a new lifting device that consisted of a lifting eye through the concrete and top flange. Second example would be, for example, the closure pore width that will never be exactly as you anticipate. Have a game plan for what to do when it's too narrow or too wide. JMT ultimately had to provide supplemental bars at some isolated locations where the 6-inch minimum lap width wasn't met at the closure pore. And finally, just overall, a good communication with the contractor and client about any issues encountered with ABC construction in the past would really prove beneficial as you begin your design on your new project. These are just a few images of our final product, the finished product, elevation views, some under bridge views, and a topside view. And I will point out that the lower right image, this is a temporary barrier that hadn't been removed yet. That's not the adjacent bridge. They're not that close together. And with that, I'd like to share a video on this project that our marketing group had put together.
This story of ABC in DC was no highway to hell. After evaluating the conditions of the bridges carrying I-295 over South Capitol Street, DDOT and JMT concluded that accelerated bridge construction, or ABC principles, presented the most practical solution. The superstructures needed replacement, but the substructures could be rehabilitated. So JMT designed the new bridge superstructures to fit within the existing site. They were constructed at the fabrication yard and delivered to the project site for installation in place. One lane at a time, the existing bridges were demolished. New bridges were brought into place, then secured by a closure core of ultra-high performance concrete and quick-setting deck overlay. Each lane was completed within a weekend, minimizing DC commuter traffic impacts. Using ABC, this project was completed as scheduled, within 6 months, with only temporary weekend detours. Thank you. Good night.
And that wraps up our presentation. So I'll open it up for the Q&A session now.
All right, thank you. Thank you for a very interesting project. So at this point, we're going to turn it to Paul Lyles to moderate the question and answer period. Paul, it's all yours.
Thank you, Torrid. We'll get everybody on here and we'll go over some questions. We have a few that came in during the presentation, and we had certainly some that came in beforehand. With that, we'll go ahead and get underway. We've broken them down into design, construction, and cost questions. And the first one we have, you may want to go to slide 28. And it was this came in beforehand. Was there any rehabilitation work involved for the substructure? You kind of covered it in your presentation. I don't know if you want to add anything more to it. You go ahead.
Sure, Paul. So I didn't really touch on this during the presentation, but we did have a bunch of substructure repairs. Crack injection and spall and delamination repairs were done throughout the abutment, stems, and the piers as well. But those were all, yes, those were all part of the project, in addition to the top of the cap rebuilds, as I mentioned here on slide 28.
Okay, and also on 29, I think you had your carbon fiber work.
Correct. That was part of the strengthening. Yep.
Okay. Next question. This one came in beforehand also. What design considerations were made to accommodate variability or tolerances in the bridge seat elevations, considering the skew? I think that's also on 28.
Correct. Yeah. So it's because we rebuilt the pedestals and the top of the cap, we were able to bring our superstructure up to the appropriate elevation that we needed. And then any other tolerances were to be made up with the LMC overlay on the deck surface.
Okay. Then on the connections between the members that you brought in, the Uhbc connections, what was the design service life for those connections?
So we don't have an exact design service life for the Uhpc, but because it is such a stronger concrete and the fact that we're sealing up that interface joint between the Uhpc and the units so that there's no water infiltration, we really felt that the actual deck concrete of the precast units would control the service life over the actual connection of the Uhpc. Ultimately, on this job, we anticipate a maximum service life of 50 years left on these existing substructure units. So that would be the critical design life left for this project.
Okay. Here's the question that came in during the presentation. And did you include costs associated with accidents? First of all, did you do a cost benefit analysis when you were picking out what you were doing?
The cost benefit analysis. So when we were first tasked with this job with DDOT, we didn't even know if we were going to do accelerated bridge construction. We went through a variety of different options from full replacement to just a redecking. The cost service study that we did really came in later as a result of the disincentive for the contractor to not reopen by the appropriate time on Monday morning. So that wasn't really considered in the very beginning. I think that given the geometry restraints on this project, we really ultimately had to use accelerated bridge construction, but the loss of public benefit study didn't really dictate that. It was more of a side study to help us formulate the contract documents.
Okay, and then the question was, did you put any accident costs or accident criteria at all in your analysis?
I would have to check and get back to you on the different criteria. Our traffic department did that study itself, and I'm not overly familiar with how they come up with those numbers, but I can find out the answer and put it in the response.
Okay. There was a question that came in. You might go to your plan view layout, and they were curious about the dimensions of the modules. I think you had about 58 feet, something like that. Yeah.
So,
and then
correct.
And what was the beam spacing? That was the other question.
So these beams here, this is hard to see. This is measured along the skew, about 7'7" on the left side, 6'11" on the right. As I mentioned, each beam had a different length and a different skew angle, so there was no real consistency between these. For the normal spacing, I would have to double check our framing plan. I don't have that in front of me.
That's fine. I was just wondering. That's what they were looking at, the length, rough length and width. That's what they were looking for, I think. Okay. Then I think that gets most of our design questions. We do have a question about the joint. Can you go to your joint detail? The question was, usually with the strip seal, they think of it as doesn't have the trough underneath. It just usually has a seal that will drain off the bridge at the ends of the strip seal. But the question was, maybe did you add the trough as an extra protection to the strip seal?
I don't necessarily think it was for extra protection. That's a good question. I don't recall the means behind the trough when we were putting this design together. I do think there was a trough in the as-built condition, and we tried to replicate what was already done. That there already was an existing downspout, so we had just kind of done the same thing, since we weren't changing the joint configuration or anything like that. Okay.
Let's look at some construction questions that came in. These are pre-webinar questions. The first one was, could you discuss the closure pour details the end diaphragm details, and the erection constructability issues for the project. That's pretty big, but you covered that in a bunch of your slides. I don't know if you wanted to add anything to that.
No, these, I think I really did touch on these in pretty good detail throughout the presentation. Yeah, the closure pour, the anchor bolts, the one construction issue that I didn't really mention, it kind of goes along with the deck over detail, was that, you know, if these abutments weren't fixed, if there was an expansion abutment, what we found was that when we were setting these units on such a sharp skew, when you would look down the line, you wouldn't see such a uniform joint line like you did at the pier, just the way that these units, you know, were set. So we were pretty fortunate that we were able to use that deck over detail, but that could be a constructability issue if you had two expansion bearings, for instance, at each end, where your joint angles weren't equally lining up.
Okay, and on the erection details, did they pick that up with a single crane and just put it out there? What'd they do?
I believe it was a single crane. I don't think I have any good pictures of it, but again, I would have to recheck our erection shop drawings. I'm pretty sure it was a single crane though. Yeah, the individual span lengths weren't overly long. I think 70 feet was approximately the longest, but on the northbound side, they were only about 50 feet.
Okay. The question that came in beforehand about could you discuss the joint details? That's the detail between the sections, and I think you covered that. I don't know if you wanted to elaborate on that any.
Yeah, I think I pretty much covered this. The only other thing I can mention is that the joint rails had to be cast slightly higher than the top of the modular unit because we had to account for the overlay ultimately. So what we had to do during the critical weekend was put down a layer of asphalt and actually plate up to this joint rail to protect it until the next stage could be completed with the overlay. But other than that, I'm pretty sure I covered how these things were installed.
Okay. And what were the challenges during the closure pour of the Uhpc? That's a pre-webinar question.
Right. As I mentioned, just the only issue that we really found was the rebar laps. I think the 6-inch minimum lap was obtained from an FHWA study. And as I mentioned, we did have to provide some supplemental bars in some locations to maintain that lap. But other than that, the closure pour was pretty straightforward.
Okay. One that came in beforehand was, what was the biggest challenge for the contractor to overcome in this project? I was wondering if it was traffic or the crazy geometry with all the angles and beams being different.
Right. No, you got both of them. Definitely the MOT, the coordination with the Malcolm X job. As John had mentioned, it was really critical, especially during our critical weekend schedule, to make sure that our MOT wasn't going to interfere with theirs. And just from a construction management standpoint, it was really challenging. And then, as you mentioned, on top of that, you have these heavily skewed units, you know, that you really need to ensure you were going to be able to get these in place within the time frame over the weekends, or you were going to be hit with that disincentive.
Okay, the final question that I have on the construction beforehand, before the webinar, was what were the lessons learned? You covered that on slide 30. I think that was pretty good. You may want to add anything. Is there anything you want to comment on that?
No, I had to think pretty hard about what to mention here, but these were the big ones. I think these were the ones that really hit home for us that I wanted to relay to everybody.
Okay. I've got a couple more questions. There's been a bunch more that have come in, and we'll get to those in just a second. But the first one, this is involving cost, and this one was a pre-webinar question. Could you discuss the effects of Skew on the cost of the project?
Yeah, so as I mentioned, each individual unit had to be detailed separately. So we had to an individual plan sheet for each of the 20 units. And I don't have the particular change in cost from the fabricator, but as you can imagine, he had to adjust everything per unit as it was fabricated. So I'm sure there were some increased costs associated with that, but I unfortunately don't have the change in the cost versus a conventional or a cookie cutter type modular unit construction.
Okay. Here's a question that came in during your presentation. Is you mentioned the disincentive or the penalty for going over the time, but was there an incentive payment to the contractor if he finished early?
No, based on the construction activities, I really think he needed every minute to get everything done. But no, there was no incentive to finish early.
It's really neat that he got done in the time y'all gave him. That was that means that's pretty good. It's really a difficult project. That's the questions that I had up until we started the question and answer sessions. And there's been a bunch more questions that have come in. I'm going to ask Jugash to come on and pick up the question and answers now.
Thank you, Paul. So the first question that came in during the webinar is asking, did you consider any other beam type other than the I-beam?
No, we really didn't. We wanted to use plakers to try and increase our underclearance on South Capitol Street, but no, it was really our plan all along to use steel beams with a cast in place deck on top to make sure these units could be installed correctly.
Okay, thank you. Next question, can you elaborate more on the carbon wrap? Any literature and references?
Sure, I don't have the exact references that we had used when we were coming up with some of our design strengths, but I can find that out and provide it afterwards. But there's plenty of ACI publications for how to design or get your required strengths from the wraps, and we basically followed those publications to come up with an approximate shear strength and moment strength that we thought was reasonable. We listed those design strengths on our plans, so the contractor or the CFRP fabricator ultimately had to be responsible for it. It was more or less just what we thought was needed for bidding purposes, but that was the extent of our role as designers.
Okay, thank you. Next question, what was the estimated construction time if traditional construction methods were used? And what was the time savings between ABC and the traditional methods, if you have that information?
Sure, so we completed this job in 6 months total, and I believe we estimated that the total construction time for conventional would be about 42 weeks. So we saved approximately 16 weeks, in our opinion, by using accelerated bridge construction.
Okay, thank you. Next question, what is the logic of using the steel beam, same as the old bridge, which had corrosion and fatigue issues, and superstructure with joints? Was jointless concrete superstructure an option that was evaluated?
Yeah, ideally we wanted to use a continuous beam and eliminate the joint, which would ultimately allow no bearings to see any water. But the as-built substructure units were they were designed according to allowable stress design, and we weren't ultimately comfortable putting such a high load onto the existing foundation and the piles. So we had to use 2 simple spans just to get a superstructure replacement to work. And in terms of the corrosion, we applied a paint layer to the existing beams, and that was ultimately DDOT's choice to use the steel beams. But as I mentioned in the previous question, there weren't any other superstructure types for this project that we really considered.
Okay, thank you. Next question, detours were discussed. I understood complete closure was not allowed. Can you explain?
Sure, so just the nature of 295 through DC, it carries a lot of commuter traffic from Virginia into the DC region. And I think John mentioned the ADT was 40,000 vehicles per day. So complete closure wasn't a possibility. Even during the weekend, it would have just flooded the surrounding neighborhoods with traffic, and it wouldn't have been possible to completely shut the bridge down.
Okay. That completes all the questions I have on my list that came in during the webinar. I thank you for your responses and turn it back to Adarad.
All right, thank you, Paul, and thank you, Jogesh, for moderating the question and answer period. And thanks to our speakers that gave an excellent presentation on a very interesting project. So on that note, we would like to conclude our webinar today. But also, I would like to remind you that there's a travel scholarship available, and deadline is toward the end of the August. So please take advantage of that. If you go to our website, the online registration is on. The early bird registration rate ends on September 2nd. Please take advantage of that. And we hope to see you in December with us at the conference. And again, don't forget to take advantage of the travel scholarship that's available. So on that note, we'll conclude and hope to have you with us the next month.